Morning, good evening, good afternoon to everyone around the world. Welcome to ACM AI's Beginner Track Workshop series. And this is workshop number 4, where we're going to be talking about multi-class classification. As usual, the link to the slides is on the screen. We've also dropped the link here in the chat. If you're using the ACM membership portal, the attendance code is CARS. And if you want to use the ACM Discord, we have a channel for Beginner Track over there. And before we start, we want to note that this workshop is going to be a little shorter because we know that everyone probably has a lot on their minds right now, and a lot of people couldn't probably make it. So we want to be considerate of that as well. So let's get started. So we're going to do a quick review of what we did last time, which is logistic regression. And logistic regression was essentially to perform binary classification. What that means is we want to bucket an object into either 0 or 1. We have exactly 2 classes, and we want to classify it into those 2 classes. What we're going to be doing this week is generalizing this to any number of classes, because that's a more real-world application. So how did that work? Well, we had this sigmoid function, which is what we call an activation function. And what that essentially did is it took a linear input and made it this non-linear curve. And that's what any activation function does. All it does is take a linear input and make it non-linear. And the particular part about this activation function is that if x is greater than 0, sigmoid of x is greater than 0.5. So the value is in this top half right here. And if x is less than 0, the value the sigmoid function returns is lesser than 0.5. So you see, you get this really nice partition or division based on what the value of x is. And this is what we're going to use for binary classification to bucket stuff as either 1 or 0. And another particular characteristic about this function is that it always outputs something between 0 and 1. And we mentioned last time that this is kind of reminiscent of probability, because what the sigmoid function really represents is the probability of an input being a particular class. The way to look at that is, given an x, how sure am I that it belongs to class 1? Or how sure am I that it belongs to class 0? Then we went further. We said that I don't want to just put x. I want this entire w transpose plus x as the input to my sigmoid function. And we said that this function is completely dependent on what w is and what b is. Because everything else is just a constant. We have an e, we have a 1, and x is just the input. So by changing w and by changing b, we end up changing the value of the function. And that's what we call the parameters of our model. W and B are what we need to learn during this process of machine learning to correctly classify X as either 1 or 0. And when we get this W and we get this B, we get something we call a decision boundary. In this case, the decision boundary
Yeah, it seems like Sudhanshu's connection is poor. Yep. Just give it a second.
Yeah, I apologize. I think I just dropped out for a second there.
All right.
Is this meeting being recorded? Yeah, okay. So I'm just going to back up a little bit because I'm not sure how far back you guys lost me. But what we're essentially talking about is that the w and the b are the parameters of our function. They completely determine what sigmoid of x is going to return. So we need to modify this w and modify this b to find the best possible decision boundary. Over here, the decision boundary was simply 0. But in a general data set, it may or may not be 0. If x was greater than 0 in this case, we get 1, and x was less than 0 in this case, we get 0. So by continuously updating W, by continuously updating D, we find the best possible values that an input X is correctly classified. And this is known as binary classification because we have two classes, 0 and 1. We also talked about this really interesting function called the loss function, which is binary cross-entropy in the case of binary classification. And it's also commonly known as log loss because we have all these logarithms going around. So to quickly review, y hat was the prediction. It is a value output by the model. So it's something between 0 and 1. Could be 0.2, 0.7, 0.5, whatever. And y is the actual true value of the sample. It could be exactly 0 or exactly 1. And it's what we're trying to achieve. And what we talked about is that when, depending on this value of y, this function ends up reducing down to something very, very, very simple. In fact, when y is 1, this term just cancels out because of the 1 minus y, and all we're left with is this extremely simple function, negative log of y hat. I mean, this is as simple as it gets, right? And similarly, when y is 0, this term ends up canceling out, and we're left with this really, really simple function. And that was it. So using this function, using this loss function, we calculated the gradients, updated the w's and the d's, and kept training our model. And that's it. So does anyone have any questions about what we just covered or anything from last week? Because the stuff we're going to be talking about this week is going to be building on this material. So it'd be good if you guys are comfortable with it.
Yeah, could you give an example of using binary cross-entropy loss?
Sure, yeah, we could do that. So I'm going to be a little hand-wavy about it, but let's say that the y hat, the prediction says the value is 0.2. And the true value, the true label I'm trying to predict was 0. So let's look at this table over here. The true label is 0. So this is now my loss function. What I'm going to do, I'm going to plug 0.2 in here. I'm going to get log of 0.8, which is, let's calculate that real quick. Log of 0.8 is negative 0.1. And if we take negative 0.1 and put that negative sign out front, we get positive 0.1. So all in all, if y hat was 0.2, y was 0, our loss becomes 0.1, which is not very much. And that's a very good thing because 0.2 is pretty close to 0, and we want to reward our model for that. Does that help?
Yeah, thank you.
Okay, awesome. Are there any other questions? You can also type them out in the chat if you're more comfortable with that. Okay. Sorry. Was W the learnable parameter? Yes, it was. So here we go. Yeah, so the W and the B are the learnable parameters. You may recognize W because it's the weight matrix. So it represents the weights of the model. Okay, I think we are good. Let's move on then. So we're going to do a poll real quick. Really simple thing. Given these tasks, which do you think is best suited for logistic regression? And this is something that we would actually use in the real world because we're given this problem and we have to decide which model to use. So I'm going to launch the poll. I'll give it about 10 more seconds. Okay, yeah, we can add it now. So I see that most of you got the correct answer, which is awesome. A few of you chose predicting the price of the house, and I think the reason for confusion might be that it's called regression, but like we discussed, we're mapping it into a continuous space, but in the end, we're just going to be rounding up or rounding down when predicting our value. So even though part of it is regression, in the end, we're going to get a discrete value. And yeah, so just to quickly recap, whenever you have something that has a binary nature, approve, deny, yes, no, 0, 1, then you want to think about logistic regression. And that's going to be really helpful in later applications. So let's move on to multi-class classification, and I'll hand it over to Adithya now.
All right, cool. Yeah, so we're going to talk about multi-class classification now. Yeah, so then you can move to the next slide. So in a multi-class classification, we have, as the name suggests, multiple classes, and we want to correctly identify whether our input data falls in one class or the other class or any of the number of classes that we have. So as we can see here, that we can think of a situation where we're trying to distinguish the input, which could be an image, into one of these classes. And you can see in front of you that we have 4 distinct classes. We have a cat, a dog, a chicken, and fish. And we assign these different classes values from 0 to 3, which is cool. I believe it's called integer encoding, but we're going to look at a better way of sort of like distinguishing between these classes. So you can move to the next slide.
Yep.
So we're gonna when we talk about multi-class classification, we're gonna use this method called one-hot encoding, which is essentially constructing your output data in the form that you can see on the screen. So we have a column vector with each row corresponding to one of the different classes we're gonna that we're trying to like classify in our input data into. So as you can see, this area of the cat would be classified as a cat, obviously, and that's why the first row, which corresponds to the cat, has a 1 next to it, and all other classes have zeros. So yeah, this as you said, this process is called one-hot encoding, and for different sort of classes, this sort of vector changes, and we're going to see that in the next slide. Yeah, so here we have the same 4 classes we were talking about earlier, but now we're using one-hot encoding instead of integer encoding to distinguish between these classes. So as you can see, the first row corresponds to the first row of the column vector corresponds to a cat. So that's why that value that row has a 1 in it, and all other rows are 0. In the case of the dog, however, we have the 1 in the second row, and everything else is 0, because the dog class corresponds to the second row of this column vector. Yeah, so I'm just gonna move on. All right, yeah. So when we did linear regression or binary classification, which is linear regression with 2 classes, this is how our model looked. We had a vector, a column vector, which containing x1 through xn, which was our input data, and we also had a column vector of the same size as our input vector, which had all the weights corresponding to the different features in our sort of model, and we had a single real number, our bias, which we used to kind of shift our output data either up or down in order to fit it better with our with the values that we actually want to get. But in the case of the multi-class model, you can move on. Our input data is structured in the same way. We still have this sort of vector of inputs x1 to xn. In this case, however, our weight matrix becomes a little bit more complicated because we are now trying to distinguish between multiple classes. And the consequence of this is that as we know from the past workshop that we've done, each weight corresponds to some particular feature of our model. The value of a particular weight tells us how important that feature is and how it affects the output of our model. But in this case, when we have multiple classes, the weight when you try to predict whether our input data falls into one class may not be the same as the weight value when we're trying to predict if our input data falls in another class. And that's why we kind of need to have this this sort of distinct weights when we're talking about all these different classes we're using. So you'll see in later on in the workshop that when our actual output from this multi-class classification is actually a column vector containing probabilities of whether we expect the input data to fall into one class or the other class or the other class, or how many other classes there are. And as you can remember previously from like a couple of slides ago, we have each row of our input data corresponds to a different class, like and that's how we sort of used our one hot encoding process. So yeah, we have a matrix of weights because the weight values for different features will not be the same when it comes to predicting whether our input data falls into different classes. And because of that, our bias also becomes a vector instead of just a single real number, because again, we have all these different classes that we need to consider, and therefore we need a bias for each particular class. Yeah, then move on. Yeah, so this is a good example. We have an image, and we construct that and modify it in a way that it fits into a vector. And this vector contains, we can say, for example, each pixel of this image in one really long stretched out vector. Moving on. Yeah, so what you do here is we have this weight matrix, and we have to take the transpose of it. And the reason for that is by convention, we have the weight matrix flipped, where we actually have the number of classes in the columns and the number of features as the rows. But if you want to multiply these matrices together, we need to ensure that we transpose the weight matrix and then multiply it with the input vector. And once we do that, we get, yeah, once we have this multiplication, add the bias, the bias vector, we get Z, which is the output. And it may look strange at first, but later on in this workshop, we're going to look at this process called Softmax, which essentially converts this output vector into a vector of probabilities, with each row corresponding to a different probability that the initial input data falls into one class or another class. Yes, as you can remember, I believe the first row corresponded to a cat, the second row to a dog, and so on. And as you can see right now, the 34 at the bottom kind of shows that our input data most corresponds to what which class that last row is representing. So yeah, this will make more sense when we talk to you about softmax, which we're going to do soon. Okay, so what does transposing a matrix mean? Okay, yeah, fair enough. So yeah. So transposing matrix essentially means flipping it. There's no real better way of saying it without sounding a little bit confusing. But when we say we want to transpose this matrix, we're essentially saying let's flip it around so that the columns of this weight matrix becomes the rows of the weight matrix, and the rows of the matrix become the columns of the matrix. And because of the nature of another better way of saying this is we can say the value that is in the ith row of the jth column of the matrix becomes the jth row and the ith column value when you apply this the transpose sort of like modification to a matrix. And because of the nature of matrices, we need to apply this transpose matrix in order to multiply these matrices together, multiply the weight matrix and this input vector. So yeah, are there any other questions? Is it just convention to organize the weight matrix so that each row corresponds to each feature rather than each column and then transpose it later? Yeah, so it is mostly convention. If you've seen from the previous workshop that we've done, we've always taken the transpose of the weight matrix when we're multiplying these matrices and the input together. And it's essentially a convention. There's no real reason to do it. We can always arrange our data to sort of be in the way we want, but that's just how it is. I'm not sure there's a real reason we do it like that. But yeah, if any of the other officers think if there's a real reason that we do it like that, then you can shout it out right now.
Yeah, it's mostly arbitrary. Maybe one way to think about it is that in the 2D case, when we had two different vectors, we need to take the transpose, otherwise we can't really multiply two vectors together. But in a high dimensional case, it doesn't really matter too much. It's how you model your problem. Yeah.
Yeah. Cool. Yeah. Also, yeah. So yeah, is Z telling us that it is most likely a fish? Yeah, pretty much. The fourth row, if I believe so, it tells us that that sort of row corresponds to a fish. And since that row has the highest value, our model is telling us that yeah, we think this is very much like, which is our input data is very much a fish. But we can also see that we have a 23 in the first row, which is also telling us that the model also like kind of thinks that our input data is a cat, if I believe the cat represents the first row. Is T a constant? No. Okay, so T is the transpose like indication. So when you have just a vector, I mean just a matrix, it's just like W, for example. When you put W to the power of T, it's not to the power, but like W to the T, that's essentially saying like, yeah, so it's a transpose operation. It doesn't really, it doesn't have a number, it doesn't have a value, it doesn't correspond to like any sort of like power. It's just, okay, we're applying this transpose operation to the weight matrix. So yeah. Hope that answered everyone's questions. Is it the same thing as a transition matrix? I'm not too sure what a transition matrix is, but I don't think it is. If any of the other officers know what a transition matrix is, but Yeah, I don't think it's a transition matrix. It's just a transpose. It's just a transpose operation, which, as I said before, kind of just flips the matrix around to make the columns of the matrix the row and the rows of the matrix the column. And yeah, okay, yeah. So yeah, this doesn't have anything to do with transition matrices. Transformation matrix. Okay. All right. So for example, transfer means if A is equal to 1, 2, 3, 4 equals 1, 3, 2, 4. Considering, yeah. So yeah. So essentially, it's just that. Like don't give it too much thought. All we're doing here is just think about it like this. You're just flipping the matrix, making the rows the column, and the columns the rows. That's about it. There's no other like sort of like fancy magic going on. It's just a standard. The transpose is just a standard matrix operation that is used in all forms of matrix algebra, matrix calculations. It's just a normal matrix operation. It's nothing fancy that corresponds only to artificial intelligence or machine learning. It's just a general sort of matrix operation. Yeah. If there are any other, I'll give it a bit more for any more questions. If you don't get any, we can move on. All right, looks like we're good. Let's move on. I believe we have a poll next. Yeah. So here's a super quick poll. Sudhanshu, you're going to be in it, right? All right, great. All right, yeah. We have. All right, so I guess most people have voted. We can start the poll. Yeah, so it seems like the majority of you guys did fine. And I guess there's a little bit confusion with the sort of the transpose operation, all that. So yeah, again, this is like a sort of a chance question. Kind of like try to like grasp your head around this sort of the concept of a weight matrix with like a lot of different weights. But yeah, so our weight matrix will have dimensions F cross C. That means we have F, the number of rows corresponds to the number of features we have, and the number of columns is the number of classes that we have. And like a very simple way of putting this is we can think that each sort of column in our weight matrix corresponds to a vector of weights for a single class. But since we have multiple classes, we kind of put all those weight vectors together to make a weight matrix. So yeah, again, the weight matrix doesn't have anything to do with the number of training samples we have. The training samples is an arbitrary value. It's oftentimes going to be very large, more than the number of features or the number of classes that we have. So yeah, that's weight matrices. If you do have any questions regarding weight matrices, you can stick around after the workshop is over, and we can talk a little bit more about it. But I believe we're going to go into softmax next. Yeah. So I'll hand it off to Jenson.
All right. I'm gonna share screen right now. All right, can everyone see my screen? All right, good. So let's talk about softmax. So like Adithya just said, the motivation behind softmax is we want like a vector of probabilities as our output, but currently we have basically the current output of our model is not like a probability. So we want our y hat to add up to 1. So what softmax does is it takes in the output vector z from our model and then converts our output into a vector of probabilities. So what if essentially happens is we take our output vector z and then we exponentiate each of the components in this vector by e. And then in order to make sure that this vector sums up to 1, we have to divide this by the sum of all the entries in this vector, which is denoted by this summation symbol. And then now we have like the activations on the right, which sums up to 1. So softmax is basically an activation function that is the generalization of the sigmoid function, which we talked about for binary classification. So if you guys have any questions about softmax, now would be the time to ask.
So is the only purpose of softmax to convert to probabilities? Is that it?
Yes. Because like what our model did for multi-classes, we multiplied W transpose by X, which is our input, and then we add the bias matrix. So that's not guaranteed to be like, that's not going to add up to 1 in like almost every case. So we want like our final output to be like a probability distribution, if you will. So yeah, that's why softmax is a good choice for multi-class classification. Does that answer your question?
Yeah, thank you.
You're welcome. All right. So the cost function for multi-class classification is cross-entropy. So the motivation behind cross-entropy is we want a general loss function that can apply to an arbitrary number of classes, C. So intuitively, we want a higher cost if our model makes a bad prediction. So that basically means if the probability of the correct class is far away from 1. So for example, if we have a cat image, but then our model only predicts there's a 10% chance that the image is a cat, then the cost will be higher than if our model predicts there's a 90% chance that the image is a cat. So the function that I just described is called a cross-entropy or categorical cross-entropy. And the formula for cross-entropy is actually kind of similar to log loss, but we're just dropping the second term. So the only class that will actually contribute to the loss is the class that's label 1. So in this case, it will be the second class, which I believe is a dog. So to minimize the cost, our model has to make like the corresponding prediction in y as close to 1 as possible, so that the log of that entry in y hat would be close to 0. All right, so like for binary cross entropy, we're summing up like the loss over all the training samples. And then if you substitute the loss function as in the previous slide, you should get something like this, which is kind of intimidating, but like if you intuitively, it's not that hard to understand. All right. So does anyone have any questions on cross-entropy?
Yeah, why do we only allow the element that is encoded as 1 to affect the loss function? Like, why don't we have a higher cost if our, like, if for instance, if we have like a picture of a cat and we have like a 90% chance that it's a cat, which is good, but we also have like a 70% chance that it's a fish, why doesn't that raise the
Okay,
loss?
That's a good question, but like keep in mind that the probability here has to add up to 1, right? So if you predict there's a 9% chance that's a dog, then like the other predictions are going to be low. So like it's kind of like measuring the same thing with the second term. So you can definitely add up the second term, the binary cross entropy, but it's kind of like measuring the same thing, if you get what I mean, just because all of the probabilities here have to add to 1. So in most cases, just 1 term is good enough, like a good enough measurement. Sorry, does anyone have any?
Why 0.27 maps to 1, like that specific value in the matrix?
Oh, actually, I think the image is, no, never mind. So in this case, our model is performing like really poorly because like y has our prediction, right? And y is the actual value. So like in this case, we're predicting there's a 27% chance that the image is a dog when the image is actually a dog. So in this case, we should expect our loss to be pretty big. So like so don't confuse y to be like y hat, because like y is the actual labeled output and y has the prediction that our model makes. So these two are not like related. But obviously if they're close, then the loss will be smaller because that means our model is doing a good job.
So to calculate cross entropy, we need to know what the actual labels are, right?
Right. Yeah.
Okay. So it's not possible to calculate cross entropy every single time because you might get like a foreign data set that you don't know the labels to, right?
Actually, in the training process, like we're always going to be using like labeled data, but like you're right, if we're applying this model to the real world, like not every image would be labeled. So in that case, we can't calculate the loss. We only know what the prediction of our model is.
Got it.
But yeah, okay, cool. All right, let's move on to gradient descent. All right, so the gradient descent is basically the same as those in binary cross entropy. So this should look pretty familiar. So why is this the case? That's because softmax is a generalization of the sigmoid function and cross entropy is basically just a generalization of the log loss. And so putting everything together, we have our cat image here, which is labeled. So this label with the 1 hot encoding. And then we're flattening all the pixels of this image into a vector. And then we're feeding this into our multi-class model, which outputs this z vector here. But this is not the probability, so we have to feed this through the softmax. So you can think of the softmax as the activation function here, and then we get a vector of probabilities that our model predicts. So in this case, our model predicts this image is most likely going to be a dog because the second class is a dog, and then we input this vector into our cross entropy, and then we compute what the loss is. Okay, I don't think the loss is actually accurate. So, but yeah, aside from that, it's basically how multi-class classification works as a whole. All right, does anyone have any questions regarding multi-class classification? If not, we're gonna do this poll real quick. All right, it looks like most people have picked 0.1, which is the right answer. So the trick here is just like all of these probabilities have to add up to 1. And so the only option would be 0.1. All right. So that's the end of this workshop. Thank you for coming. Please remember to fill out our feedback form because your input is always really helpful to us. And next week, we're going to cover KNN and Python. I know last time we said we're going to cover KNN this week, but then we wanted to make the workshop this week like shorter because of the midterms and the election. And remember, the event code for today is CARS. And make sure to follow us on Facebook and GitHub. We'll be posting our slides on GitHub as well. If you have any more questions, feel free to ask.
Awesome. Thank you for coming.
Yep.
Everyone in
Thank
the
you guys.
chat.
Thank you guys for coming.
Also, for the benefit of the recording, we're going to be covering Python next time. We know a lot of you people mentioned that you were unfamiliar with Python, so we're going to be walking through the basics next time. So definitely look up for that workshop. Were there any questions?